Uh, the title of my presentation again is, an intelligent integrity monitoring system for pressure boundary components and the piping operating at high temperature in creep range. The outline of my talk is, as you can see, first, introduction. Second, issues and the solutions on integrity of high temperature components. Components in creep range. And next, elevated temperature design, ETD, rules and issues. And next, development of a high-tech platform and the verification of the programs. High-tech WIMS, which stands for high-temperature evaluation program of a web-based integrity monitoring system for high-temperature application to the high-temperature pressure boundary components. And the application of a high-tech to high-temperature facility. And I will summarize my talk. Let me start my talk with pressure introduction of a pressure vessels and the piping that are subjected to severe loading conditions at high temperature in creep range for the systems of generation 4 reactors, fusion reactors, supercritical and the ultra supercritical thermal power plants, and the renewable energy facilities, such as a thermal energy storage facility, which often has the design temperature up to 750 degrees C. Yeah. By the way, there are issues on integrity of components, and that there are various kinds of causes and defects and the cracks which are detected, especially after elapse of some operation time rather than at the end of a construction or startup. Those problems are such as design problem, fabrication or installation problems, and the material problems. Then how can integrity can be enhanced? There could be many ways, such as development of new materials and applications, application of improved ND techniques, and many other ways could exist. By the way, those methods are quite expensive and time-consuming. As an alternative and a promising way to improve the integrity of a pressure boundary components subjected to high temperature in the creep range, we can think of the two approaches from viewpoint of a designer and the operators. One is application of a high reliability nuclear design rules. That is nuclear design rules on top of the conventional design rules, such as ASME Section 8 Division 2, which is for the pressure vessel, and the ASME P31.1, which is for power piping. I mean that they are conventional pressure vessel and the piping, but if you apply on top of the conventional design rules, if you apply nuclear design rules, then reliability of the pressure vessels on the war piping could be pretty much enhanced. And the second approach we can think of is the application of intelligent monitoring and the lifetime management for for higher reliable predictive maintenance for the system. Let me talk about the elevated temperature design rules and the issues for pressure vessel and the piping. First, let's have a look at the nuclear grade design rules for pressure vessels. The representative ones are ASME Section 3, Division 5, subsection H. From now on, I will call it as a ASME HP. And the other one is the French high temperature design rules of RCC MRX. And RB 3200 is for pressure vessels, and RB 3600 is for piping. And the important thing for the nuclear design rules here is that the 4 limits that should be satisfied in design of high temperature components the four limits, that is stress, strain, fatigue, and creep fatigue limits, should be satisfied so that the designs are to be satisfied. In the meantime, in case of non-nuclear grade pressure vessels and the piping, the representative one for pressure vessels in conventional power plants or facilities like a refinery, ASME Section 8 Division 2 is the most commonly used design rules for pressure vessel, while ASME P31.1 or 31.3 are commonly used for the design of a piping for non-nuclear grade design rules. Now, by the way, the important thing here is, in case of a non-nuclear grade, only two limits are required to be satisfied. That is stress and the fatigue limits. And in the meantime, strain and the creep fatigue, those are the requirements in nuclear design rules. But in non-nuclear design rules, these two limits are not necessarily satisfied in this design. If we have a look at in more detail for the design rules, in case of the representative high temperature design rules of ASME HP, Section 3 Division 5, depending on the metal temperature, we can apply ASME MB for light water reactor and ASME HP for generation 4 reactors. By the way, as explained, the limits on stress, fatigue, strain, and creep fatigue limits must be satisfied for this design to be satisfied. And just like the case of ASME HP, this is also the nuclear design rules about French RCC MRX. And depending on the loading type, type P and the type S damage, should be analysis evaluation should be conducted. By the way, as can be seen here, the four limits: stress, fatigue, strain, and the creep fatigue here. Fatigue, creep fatigue, strain, and the load control. All these four limits must be satisfied in these design rules of a nuclear grade. In the meantime, in case of a non-nuclear grade, which is ASME Section 8 Division 2, in this design, by the way, originally these design rules were developed for the application of a low temperature design. And as the components operating temperature has been increased, it has been extended to be applicable to the range of high temperature in the creep range with a slight modification of the maximum allowable stress. And the important issue here is, as explained before, only stress and the strain fatigue limits are required to be satisfied, while strain and the creep fatigue limits are not necessarily satisfied in this approach. Just like this case of ASME Section 8 Division 2, in case of the non-nuclear grade P31.1 for power piping, also it has been originally developed for the design rule of a low temperature under creep range. And it has been extended to high temperature in the creep range. And similar to the previous case, the two limits on stress and the fatigue are required by the design rules, but strain and creep fatigue rules are not required to be satisfied in this design approach. So it would be necessary to perform additionally a nuclear design rules to enhance the integrity of a design of a pressure vessel or piping. So in our research institute, in my project, we have developed a high-tech platform, rather comprehensive program, design evaluation program, and we have conducted verification of the programs. It is, as explained before, it's a rather comprehensive design platform. HITEP stands for High Temperature Design Evaluation Program, which covers design, integrity evaluation, and the lifetime management, like creep fatigue monitoring. Here, if you click here, actually it is composed of three modules. This is a HITEP nuclear module, which is composed of the 5 design rules. And the central part is HITEP non-nuclear, which is composed of two design rules, and the third one, which is say main topic of my presentation today, is a monitoring system, integrity monitoring system. And let's have a look at one by one briefly. In case of HITEP nuclear design, here, if you click here, you will be linked this window, which is composed of the 5 design rules of ASME-HP, French RCC-MRX, and the ASME N898, which is for alloy 617, for the application of very high temperature gas-cooled reactors, and the ASME HHA, which is the design rule for graphite components in ASME code, and the ASME-MB for light water reactor application. And if you click the relevant button, then you'll be linked to the relevant evaluation sub-program. And in case of non-nuclear design rules, if you click the central button, then you'll be linked to this 2 design rules of ASME Section 8 Division 2 and the code case N2843. By the way, this code case 2843 is the code case to this Section 8 Division 2. And basically, this approach is the approach of ASME-HP of nuclear grade to enhance the reliability. And associated with verification of those programs, it's very important to verify those programs. The method that we conducted for the purpose of verification, a comparison of the 2 results from this HITEP program and versus a direct hand calculation, independent calculation with Excel. And we compare the 2 results. And for this HITEP RCC-MRX, we also conducted third-party verification as well. And this is the actual case of reactor vessel, which has been designed and installed in a large-scale sodium test facility, which has been constructed in our research institute. You can see that the 2 results are in good agreement. And in case of ASME-HP, as you can see, the 2 results from HITEP and the direct calculation with the Excel is in close agreement. Let me talk about, from now on, the web-based integrity monitoring system. As explained, it is composed of a number of buttons which activates the data processing or calculation. And the concept in concept flow diagram is data processing stress analysis based on Green's function approach for thermal stress and the integrity evaluations according to the relevant design evaluation, and the maintenance of lifetime, such as the evaluation of remnant life and optimal maintenance time. And these are the buttons you can see. And if we have a look at each button, this is uploading the operational data such as temperature, pressure, and flow rate, and the Green's function-based stress analysis for the thermal stress calculation, and the evaluation of current status on creep fatigue damage. If the results are here located, then it means within the damage envelope, so it means in safe region. And associated with the remnant life, this is the remaining part. So depending on your policy, at what time you will perform maintenance. If you want to perform maintenance in 50% of a damage, then you can use this cursor, then the time will be shown, and you can follow the time. This is the application of the HITEP platform to high temperature systems of a large scale sodium test facility of Stella 1, Stella 2, and the test facility. And these are the components where we have applied the HITEP platform. These are the actual components and the systems that HITEP was actually used in design and the constructions. This shows the case, and this is something different because the material properties are not available in the design rules for the stainless steel 316L. And this is the actual application of HITEP beams to the thermal power plant with the steam piping. Due to lack of time, I'll skip. And then let me summarize my talk. HITEP platform is composed of 3 modules, and we have conducted verification. And again, the elevated temperature rules of a conventional rules could be non-conservative in case of a long-term operation in the creep range, and the nuclear design rules should be applied in that case. And the HITEP WIMS can be used for reliable and efficient monitoring on integrity of high temperature components and the piping as per nuclear design and non-nuclear ETD rules, elevated temperature design rules. Okay, that's it. Thank you.